All right, let's go for that Stokes theorem, which was giving you problems, so that we just polish it before other questions. Are you still there?
Yes, I'm here.
Yeah, so this one was the question paper for 2024, first
October.
one, which we're supposed to do number 7.
So did you have a recording where we did number 6, the one we calculated the area? You have a video for it.
Yeah, you just tell me the date, then I will just check here. All recordings are there.
I forgot the date. I was trying to check. I don't remember the date for that one. I knew it was something about but it's fine. So that one, then, the only problem that I have is number 1, the sketch.
Yeah,
That is
we are
fine.
going.
You can redo everything. I mean, there's no harm. Part of learning anyway.
So the question is saying state the theorem by converting the flux integral over a bounded surface to a line integral over the curve that bounds. So for A, here we want the bounded surface to a line integral over the curve that bounds the surface. So it's just by definition, the Stokes theorem. So they want you to rewrite the formula. Remember, we are not given this formula. Hello?
Yeah, yes, I'm here. They are not
Yes.
given.
Yes. So state Stokes theorem. Stokes theorem states that the flux of a curl, you see that C which is written here, the flux of a curl. The curl which they are referring to is this C, this curl.
Oh, yes.
The curl of vector F through a surface S. So the vector is F through a surface what? S is equals to the line integral, which means it's equals to the line integral of a vector field. So that vector field is still F over the boundary curve, that boundary curve of the surface, from what to what. So you should be in a position to define at least this. However, the statements, they may differ from textbook to textbook, how they define Stokes theorem, but the formula itself, it does not change. It's just the same. The words may be different here and there, so you just find the ones that you remember in the exam. So that surface S and the vector field we are given, you can see that grad cross F. Can you see? The grad, this grad cross F,
Yeah.
cross F. And this one, it's a dot, yeah, dotting, grad cross F dot ds. ds is just a change. ds is just a change. Change in S, change in S. Change in S, we represent it in integral, it's ds, change in S, ds. So whenever they are talking of change in S, they're referring to ds. dr, change in R, that's what it means. Grad, then the grad is facing the other way around, which means the partial derivatives. The partial derivatives. So which means with this one, which it is saying just by stating, which means you can score 6 marks. So it's something that you should remember this one. Will it be a challenge?
No. Nah.
Yes. Remembering, can you see how many marks here? 6.
6, yeah.
And it comes, and you know it's going to come.
It's going to come, yes.
So you can't miss these ones. You must sit down, polish up from the Stokes theorem. State that the flux of a curl over a vector field F through a surface S. So we are just interpreting this one. What is written there? The flux of a curl of a vector field F through a surface S is equals to the line integral of the vector field F over the boundary curve of the surface. Then you state that equation. We are done. Where there's a dot product, where there's cross product, and remember that F, they are vectors. It's only that the gradient, the grad, like this. They are also vectors. That's why you are crossing. Grad cross F. F is also a what? A vector. So don't forget that. F is here it's in bold because bold, it simply indicates that. So dot, don't forget the dot. Dot product now of ds, which is the same as that integral in terms of writing. So we must be in a position to write this correctly. This is a vector, F, dot dr. So dr, that vector, like that. Any question, how you write it? Dot dr. And obviously there are integrals there over that surface. All right, let's move on to the next question. So the next question now is saying, consider this surface S. Consider the surface S. So that is our surface S. X, Y, Z, they're an element of R3, which means in R3, from linear algebra, R3, you can see 3 coordinate system. So S is an element of R3, 3 coordinate system. And also, we are given that x squared plus y squared plus z squared is equals to 13. But that z, this z must be always greater or equals to 2. So that is the condition that we are given. Z must be greater or equals to 2. So that above. And assume that S is oriented upwards. Let C be the orientation boundary of S. From our definition, the orientation boundary, which is that C. The orientation boundary. From our definition of Stokes theorem, that's C, the curve. Okay. So first, sketch the set S in R3 and show the orientation of the curve on the sketch. All right. So we are given this equation. What is the equation of a circle? Hello? Ivy? Are you still there?
Yes, I'm here, sir.
All right. I'm saying at matric level, the equation of a circle, how did we find the equation of a circle?
Isn't it r squared equals to x squared plus y squared?
Yes, we used to say r squared is equals to x squared plus y squared. That was the equation of a second. R squared is equals to x squared plus y squared. That was the equation of a second. All right. And if that r squared is going to be equals to something there, then you know that will be your radius squared. So similarly, we are going to use the same concept when applying to this sketching. So you need the equation to know this equation, it represents what. So let's start. So here, sketch the set S in R3 and show the orientation of the curve on the sketch. For example, the surface S is part of a sphere. So this is part of a sphere. So the equation that we are given is equation of a what? Equation of a? Hello? This is equation of a?
A sphere.
Yes. For R squared, it was a circle, isn't it?
Yes.
Now, and also for a 2D shape, it's ending with the x squared plus y squared is equals to R squared. But this one is now in 3 dimensions.
Oh.
X squared plus y squared plus z squared is equals to 13, which is your R squared.
Does it mean that when a circle is in 3D, it automatically becomes a sphere?
Yes, that's correct.
Oh. Okay.
And that z of that sphere, we are only taking for z greater or equals to what? To 2. So which means we are not including the surface. If that sphere, the inside, it's the upwards of that sphere. Remember, it to be the z going upwards. So which means we are only taking from z equals to 2 up to z equals to 3. I mean, from z equals to 2 going onwards. So suppose this is z equals to 2, then you take only the z equals to 2 going upwards. So we are not taking anything less. So if this is z axis, which means I'm starting at z equals to 2 going upwards. So starting from that surface, going upwards, going upwards. That's what they mean.
Is that z equals to 2 given in the equation?
Yes, it's given here. We are told that it should be greater than what?
Oh.
Should be greater than.
Mm.
And remember your axis, your axis will be somewhere there. The z-axis, it will be down, or the x coordinates. So we find out this will be x, this will be y, and then that will be z going upwards. So we find out the axis, they will be somewhere there. The axis, they will be somewhere there. So this is x equals to 0 at this point. Then you find out that this, where they want this region, it will be somewhere above the xy plane, somewhere above the xy plane, because we are talking of the xy plane. This is our x, and then this is our y, then the z is up. So you can see that part is now above the xy plane, going upwards. So for z greater than 0, greater or equals to 2, sorry, the boundary curve C is the intersection of the sphere and the plane. That plane is z equals to 2. That is the plane which they are referring to, the intersection of z. This intersection is a circle. The orientation of S is upward, so the orientation of C is counterclockwise, which means anti-clockwise. What do they mean? If the orientation of the surface is upwards, then the orientation, it will be anti-clockwise, always a curl. If the curl is oriented upwards, the orientation of the C is always anti-clockwise, which means it's moving anti-clockwise. That is the orientation of your C. And if the curl is if the orientation is downwards, then the curl is clockwise like that, clockwise direction. That would be the C. Any question there? Any question? If the force field, by orientation, they mean the vector field. If the vector field is facing upwards or it's going towards up, no. Remember the right hand rule. You still remember the right hand rule? Faraday's law? Hello?
Yeah. Hello.
Where the thumb is facing upwards, isn't it? Right hand rule. And the direction, it will be anti-clockwise of the other fingers. They will be facing anti-clockwise, which is, yes, counterclockwise. Then when you face the thumb downwards, that is the force field is now, orientation is down. The direction of the other fingers is what? Clockwise.
So if it's facing down, it's clockwise. And then if it's
Yes.
facing up, it's anti.
Face the thumb upwards, it's anti-clockwise. The direction where the other finger will be rotating. That's how you interpret that. But the question here is saying that. The question here is saying, let's take the surface in R3 and show the orientation of C on a scale, which means that surface S, then the orientation of C, which means you are referring to it that this is anti-clockwise. For example, our sphere, which we have drawn here, which means if you are talking of the curl, that region C, which means you are referring to it as anti-clockwise. If the force field is going up, then the curl will be anti-clockwise. Let's use a different color. The curl in green, which is anti-clockwise. Anti-clockwise. So if we are moving upwards, the curl, the integral of C, that curl is anti-clockwise. Why? Because that force is going upwards. And if the force is going downwards, the force field, which means it's clockwise, the curl will be clockwise. So in our situation,
Where is in the question is it saying that the force is going downwards? I mean
or
upwards.
the orientation, yes, they stated it here, let C be oriented boundary S. So assume that S is oriented upwards.
Oh, okay. So yeah, I need to be on the outlook for that. Because
Yes.
the reason is what it means.
Upwards, no, your curl is anti-clockwise.
Anti-clockwise, yes.
And then if it's downwards, which means the curl is what? Clockwise. You'll be moving like this,
Yeah.
which is your C. So that's what they want to see. So which means on your diagram, you show the direction of the curl. We've drawn from Z equals to 2. So remember, this is Z. Z equals 2. Then you indicate the curl by arrows. That is, for Z equals 2, it's counterclockwise. It means the arrows, they are opposite that, counterclockwise, opposite the direction of the clock.
So
That is
Most of these diagrams, they need to be above the axis.
Yeah, because they know it's if they go exactly on the surface, it's easy. They just want to see whether you've shifted it up. So once you draw the XY plane first, you indicate. Once you see when they see that you indicated XY plane, then you have shifted the graph upwards. Already it's an indication that it's above the XY plane. So now the ones for the calculations. Find a parametric equation for C. So this is just calculation. It's not difficult. For the parametric equation for C. That's what you are doing. Find a parametric equation for C. Let's go to the curve is the circle formed by the intersection. The intersection of this sphere and Z equals to what? Z equals to 2. Z equals to 2, the plane. Remember a plane which passes Z equals to 2. A plane which passes Z equals to 2. Remember, if it's like this, a plane, if you are having X and Y, a plane, it's something that is parallel to discs. So it's parallel to those plates, those axes, which is passing through Z equals to 2. So this is the plane which they are referring to, which is cutting at Z equals to what? 2. So that's a plane. And that plane is parallel to the XY plane. Cutting. So it will be cutting what? That sphere. Remember, we have drawn a sphere. So it's cutting through that sphere at Z equals to 2. That is the intersection of the sphere and the plane at Z equals to 2. So substituting Z equals to 2 into the equation of the sphere, Z equals to 2 into the sphere equation, because the difference between the equation of a circle and the equation of a sphere is just the added Z squared here. For a circle, it's only have X squared plus Y squared is equals to R squared. But for a sphere, now it's X squared plus Y squared plus Z squared is equals to R squared, which is the radius. Okay. Any problem there?
No.
So we want to find the intersection. So where there is Z on the normal equation of the sphere, you substitute with that Z equals to 2 into the sphere equation. So this, what does it give you? Where there is Z, we have put what? A 2. We are just finding where they meet. What are the equation where there's that intersection? We want to know what would be that equation of that circle where they are going to meet, where you are going to find those parametric equations. All right. Now we have replaced Z with a 2. Now the equation comes back to equation of a circle. So X squared plus Y squared plus 4 is equals to 13. And then you simplify. X squared plus Y squared is equals to 9. Therefore, in the end, you know that this is 9, which means it's X squared plus Y squared is equals to R squared. R squared is the radius squared. So 9 is equals to R squared. If I want R, I'm going to say square root of what? Of 9. So the radius is a circle of 3, where the plane intersects with that sphere. And the center, we know the shift, this one, in terms of the standard, it will be x minus 0 bracket squared plus y minus 0 bracket squared is equals to r squared, which is 9. So your r squared would be 9. So since this is 0, this is also 0, which means the center, it's centered at 0, 0. But where that z plane was cutting through that circle, it was z equals to 2. So which means here on the diagram which I drew here, can you see this diagram which I drew?
Yes.
Yes. Mm-hmm. So which means the base, this surface, that is the equation of the circle, where the plane cuts, that plane cuts that sphere at z equals to 2. So which means the bottom surface is the one that is going to be the equation of the circle of radius 3. So the radius from the center to the radius is 3. Now that you have found your equation of the line of intersection, everything now we start to parameterize, which means a parametric equation for a circle of any radius r in the xy plane. So now we only want that strip which we have colored there in green. That is the strip that we are only interested in, that one. That surface only in green, this one, which means it's intersecting only that strip. That is what we are interested in. That strip which is having a radius of 3. From there to there, 3. There to there, 3. So that is the one which we are only going to deal with when we are calculating the parametric equation. All right. So any parametric equation for a circle of radius r in the xy plane. R of t as a vector. Remember that r in bold is a vector. R of t. R of t. The x coordinate of r of t and the y coordinate of r of t, that vector, is given by r cos t, and the y coordinate is given by r sin t. This one you must know it by head. That for x coordinate, for a parametric equation of a circle, if I want the x coordinate for a parametric equation, which means it's r cos t, the other one for y, r sin t, which is not difficult. So for the curve C, the radius is 3, and the z coordinate is what? Is 2. The orientation is counterclockwise, which means anti-clockwise. So we can use the standard parameterization, which says that now that's where there is the change now of values here. I want you to check. R of t, remember we said R of t, it's x, y, and what? And z, isn't it? Hello?
Yes, I'm here.
Yes. 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 So R of t, remember we said R of t here. If you want to parameterize it, it's R. The general for x coordinate, it's R cos what?
Cos t.
Cos t, comma. R sin t, the y coordinate. R.
And that one
Then
is
the z coordinate. The z coordinate where it intersects the x, you say it's what? Z equals to
2.
Yes. So those are the things that you must take note. The R of t does not change. It's always the same. Equation of the same. Always the same. Then we come to what we always do. This is a second. When you talk of radians, we are starting from 0. Here you go to pi over 2, which is 90 degrees, pi over 2. From pi over 2, you come to pi. When you come back, remember we say it's anti what? Anti-clockwise. So your path is like this. You indicate with those, that is your path. Anti-clockwise, the arrows, anti-clockwise. So starting from 0 degrees to 2 pi, which means 360 degrees. That gives us that second equation of a circle. And that circle is having a radius of what?
Of 9.
What is the, no, the radius is not 9, but the radius is
3.
Remember, equation of the circle is r squared. So 9 was the r squared. So if you want the radius, that's when you say square root of r, like what we did. R squared was 9. But if I want r, I make square root of 9. So now you just replace your values. Where there's r, you put a 3, which is this 3. Where there's r, you put a 3. Right. The x coordinate, you have been told that it's cos what? Cos t, the general. Where there's r, you are just replacing, since now this circle is having a circle of radius what? Radius 3. Where there's z. So this is now the standard parameterization of the equation of r. But you must tell us t. T must range from what to what? Your t. So my t, where I am saying cos t, that argument is any value from t, from 0 up to pi over what? Over 2. Do you understand that limit, my t?
Pi over 2 or pi, 2 pi.
0 to 2 pi, yes. Is it a problem, that one? That it's a circle which is starting from 0 degrees and ending at 2 pi, 360 degrees. Is it difficult?
Yeah, it's a problem.
It's clear, isn't it?
No,
Yeah.
it's not clear.
All right. Yeah?
I need clarity on that. It's not clear.
It's not clear.
I think you said the radius, no? It's ranging from 9 to...
The radius is 3. Is the radius fine?
The radius, which is, I mean, on that circle, you see that circle which you draw there with the green thing.
Yes, the radius is 3.
Yes. It's moving from 0 to pi over 2, which is 90, right?
Then from pi over 2 to pi.
Which makes it 360.
Then from pi over 2, from pi over 2 to pi, then from pi to 360 degrees. That is why we are saying our range of t. Range of t. Remember, t, instead of putting theta, when you do parametric, we use t. We don't use cos t, cos theta. We normally use t. So instead of them using theta, they are just saying the theta is ranging from what to what. So in our, the theta is ranging from 0 to 2 pi.
360, yeah.
Which is 360. So instead of using theta, they are using t. So use now Stokes' theorem to evaluate the flux integral. So everything has been set. Here, for the second question, remember what we were looking for? The question was saying now, find the parametric equation for what? For C. Can you see? Find a parametric equation for C, which is number. So parametric equation which you are looking for C, it's always given in terms of R. You must have this equation, that parametric equation, to say what is R. Remember, we are going to say dr. So you should know what is your R first. So my R is always, my R, that parametric equation, it's always R cos t, R sin t, and Z, where you want to cut the plane. And you must know the t is starting from 0 to 2 pi, etc. So already now we have our R of t, which is the parametric equation. Any question there? How we obtain the parametric equation before we evaluate? Because it's going to be repeating these things now and again. So once you know the one problem, you'll be able to do the other one. Any question on how we find parametric equation? Parametric equation, it's, in other words, they just want what is R of t in terms of t, not R theta, but R of t. And when you have your R of t, you give us what t is ranging from what to what. The t is ranging from 0 to 2 pi. Then you are done. Your 6 marks you have collected. Any question before we go? Before we proceed?
No.
All right. Then now for the third one, use Stokes theorem to evaluate. Now we want to evaluate that integral, which we stated at the beginning. According to Stokes theorem, we can evaluate the flux integral as the integral over that surface, which is the grad cross f dot ds, by calculating the line integral of the curl, which means it's f dr. I know r, and I can be in a position to calculate d what? dr. And the curl of that line, I know it's from 0. The curl, how is the line curling? It's from 0. This is the curl of the line. It's a circle. It's from 0 up to 2 pi. So by curl, we are meaning the direction of those lines. From 0 to 2 pi, they are moving in a direction of a circle of radius 3. So you set up your integral like that. So given the vector force field, that one was given. When you are now evaluating, remember, it was given. Let me show you. Before you evaluate, can you see? Let f be this. Before you start to evaluate using Stokes theorem. Any question?
No, I'm listening, sir.
Yes, but did you see where it's saying f of x is y negative x 2z? So f differs. Some of the time it can be any number. So you should be in a position to know which f is given. So that is our f. So how are we going to use that f now? That's what we want to do. For number 3, using Stokes theorem. So R, we found our parametric equation, R, cos t, R sin t, and z. Now we are using the Stokes theorem. From the Stokes theorem, we are having the vector field F, which is x, y, and z. X is 7. X is 7 units, or y units in the x direction, minus x in the y direction, and 2z in the z direction. And the parametric equation for C, now we are using it now, the parametric equation for C. The parametric equation for C, this is the parametric equation for C, which we have calculated above, where 0 is ranging from, t is ranging from 0 to 2 pi. And how do we find first f in terms of t? Can you see this f which you are looking for, this one? I want to find that f in terms of t. And remember,
The one with
like, yes, this f which you are going to put there is the same f with this one. But you don't write this f which is given in the values that were given. You must write it in terms of what? Of that t, which is the parametric equation. So you are simply converting that f which was given on the question paper. F is y minus x 2z. So we are converting that f into t, into variables of t, which are the parametric equations. Any questions?
No, I just want to see how. Because I thought we used that one that we're given.
Eh?
No, I'm saying I don't have a question, but I want to see how we're going to do it. But to me, I thought I was going to use that one. Remember, I told you that I attempted this question. So I want to see how.
Yes. It's a matter of just yes. So now, all right. So let's go to F. If our parametric equation. So we are saying, can you see the equation of y? They are saying f of xy is y negative x, this one. Are you seeing this? Hello?
Which one?
Yes. So the equation which we're given, which you want to change from x to t, is this equation for f. So where there's y, remember this is x coordinate of the parametric equation. This is y coordinate of the parametric. This is z coordinate of the what? Of the parametric equation. So where there is z, you are going to replace z with 2. So which means z here, you put a 2.
On the
And
given equation.
minus x, you are going to replace x with 3 cos t, y with 3 sin t. Any problem there?
Oh.
So it's a matter of now rewriting that function f, which was originally in terms of variables x, y, and z. And then you rewrite. Now you find your what?
The integral.
Before you find the integral, you find the function of what?
T.
Find the function of f, isn't it?
Hello.
Yes, I'm waiting for you if you have found it. The logic behind it. Are you understanding?
To find the function of T.
Yes. So now once you have found now we are rewriting that f in terms of t. So we are rewriting that f in terms of t. So where there was that f, we are replacing in f. In f, we are putting values of what? Of r of t, which is that parametric equation. So where it was saying originally, where it was just saying x, y, and z, you replace x, y, and z with those variables for r and t. Any question?
No, that one I understand. You are placing the parametric equation to the given equation.
Yes. Then thereafter, you find the derivative. The derivative of r. When you differentiate cos, r3 cos t, what do you get? I'm saying now we are calculating the derivative of r.
Minus 3 sin t.
Remember our r of t as a vector was equals to that square bracket. It was 3 cos what?
3 cos t.
And 3 what?
3 sin t.
3 sin t. And then the last coordinate is?
Right, it was 2.
Which is 2, which is a constant. It's no longer just z, but it's a constant.
Yeah.
Then you close your bracket like that. It is a vector. So if I say differentiate 3 cos t, what do you get? Differentiate a cos,
it's in minus sign,
which is minus 3 sin t. And what if you differentiate sine? When you differentiate sine,
it's 3 cos t.
for sine, you just get a positive. If you differentiate 2, you get what?
Yes.
When you differentiate 2, you get 0, isn't it?
Yes.
Yes. So now that what we are referring to as r prime t. This is what we are referring to as dr. Now, do you know that dr now? where we are going to replace dr, we are going to replace dr with this one, which is r prime dr. Any question?
No, nothing.
So now, after we've found our function in terms of t, now we are going to dr. Find the derivative of r. Find the derivative of r. So by solving f dot r dot t, which means this is a dot product, which means you have f, you know f. What did we say f is? F in terms of t, it's 3 cos, 3 sine t minus, yes. So which means f dr. After you've replaced, now you want to find f in terms of t. What is the simplified one for f in terms of t, which is 3 sine t minus 3 cos t and then 4. You are replacing in the value of what? Of the original that was given. Remember the original that was given for f, it is 2z. It is 2 what? Z. And as we found that z before, it was just 2z. And you are going to multiply the z plane of z equals to 2, which means z plane. The z plane, z equals 2, you substitute. That's why now it's in terms of parametric equation is 3 sine t minus cos t, and the z coordinate is 4. Now after you are done, you find the other derivative, which is that compute the dot product. What is f dot r dot t? If you dot product, which means the first column times the first plus the second times the second column plus the third times the third, then that's how you do dot product. So dot product, after dotting, you find that it's minus 9 sine squared t minus 9 cos squared t. All right. So let's expand f dot r prime t. Why are we doing this? Check the formula. F multiplied by dr. So if I have f and r prime t, f and r prime t, which means I'll be done. F in terms of t and r prime is also in terms of t. So when you get f dot product, we are going to get it's minus 9 sine squared t plus cos squared t. Then you factor out the common factor. You factor out the common factor. What are the common factors so that you can have an identity? You take out sine squared minus 9, sine squared plus sine squared, you factor it out. T plus cos t, we know it's 1 from metric. So once, and here, what are we solving here? We are solving this one.
No.
Yeah, dot. First component of f. First component of f, which is 3 what? For f, we say it's 3 cos what?
Cos t.
Yes, 3 cos t. But here, the coordinate of f, remember the coordinate of f, if you go to f, it's saying what? What is the coordinate of f here? It's saying y. Can you see? The coordinate of f is saying y. So in terms of parametric equation, we said y is 3 sine what? Y 3 sine t. That is the, so which means here, that is the the value which was there. It's 3 sine t multiplied by the first component of r. Remember dot product. Then the first component times the first component plus the second component, it's minus x. Minus x in terms of t, it's minus 3 cos t times the second component of the derivative of r. That's why it's minus 3 cos t times this one. The last component for x, I mean for f, was 2z, which means 2z is 2 times 2 in the z plane. This is the 2z, 2 times 2, which is 4. So when you put it, it's going to be 2 times 2, which is 4. That's why on the z plane, they've given us 4 here. 4, which means for f, it's 4. But for r prime of t is 0. That's why it vanishes. Then it's simplify negative n squared, factorize everything. We are going to get 1 plus t squared is equals to t. Then is equals to 1. So you simplify. Since we know that identity, the answer there is negative 1. And what is it that we are evaluating to negative 1? Negative 1, negative 9 times 1 is this value. F as a vector multiplied by dr, like multiplied by dr, which is prime, dr prime. Or it can be dr only without the prime, because r prime is equals to dr. R prime is equals to dr, which is that change. So once we calculated that this is f dot r prime, this is what we are going to get. If we dot f dot r prime is negative 9. But we are not done. Once you get, now you need to come, now you evaluate. So if the formula says integral over that curl of f dr, what is dr? This is the one which I was telling you, it's r what? R prime. So which means the circle, that curl which you said it's anti-clockwise, which is moving anti-clockwise, that is the curl. That is the curl. It's ranging from 0 to 2 pi because it's a circle. And that force, that vector field, F, is given by f dr dt. Okay, f dr dt. Then from there, you have your integrals, so you need to simplify. What is r prime? R dr dt. What is r dr dt? We have already calculated it was negative 9. It was negative 9, which means the whole of this, we calculated it first. Why are we putting dt now? Why are we putting dt? Because our limits for parametric equation, we are moving from theta to t, which means the t was ranging from 0 to 2 pi, not theta. That's why you are putting dt. Then,
so if it was anti-clockwise, was it gonna also range from 0 to 2 pi as well? If it was clockwise?
If the orientation was
clockwise.
If the orientation is
clockwise.
Hello.
Yes, clockwise direction.
Oh, it's only a sign that differs, differing with the sign outside. Negative. Hello. If it was clockwise, then you just compensate with a negative outside the integral.
Oh, okay.
Yes. Is it clear now?
Yeah.
And then from here, it's just a matter of integrating from 0 to 2 pi. What is the integral of -9 with respect to t? What is the integral of -9 with respect to t? So which means even if you put the integral outside, the integral of -9 with respect to t, which means it was originally it was -9t. After I differentiated -9t, I get -9. So the integral of -9 is -9t. Then you put the limits from 0 to 2 pi. You subtract. When you subtract, we're adding. First, we add the 2 pi. That's why it's -9 times t, where the t is 2 pi. Then this is for subtraction. You're subtracting the upper bound minus the lower bound. Minus 9 times 0. Then you get -9. Then your answer becomes -18 pi minus 0. So the answer is simply -18 pi. So I have chosen another similar question from that one which you sent me today for Stokes theorem, so that you can compare and contrast. This is the one which is here so that you can practice. Can you see this one, number 10, for that question which you sent me for February 2024?
Yeah.
Yes, and I've provided the solution again. So we are going to be following this. I've provided the solution, state the Stokes theorem, everything is there. Mathematically, what does it mean? It means that, and then sketch the surface, evaluate. But now, we have been told that Z, can you see the Z now? Z is less or equals to what?
9.
Z is less or equals to 9. Can you see it? So what tells you if Z is less or equals to 9? The orientation, it's facing what now? The orientation is facing? What would be the orientation for this one? For this question?
Can I see the question?
Where is the question? Where is the Z going to be? If Z must be less or equals to. At that time, you cut, you see your sphere was like this, mate. At that time, your sphere is going upwards. That is the sphere, it was going upwards like that. But this time, the sphere is starting, must be less, going downwards. It means the orientation, it will be downwards. So your Z is less or equals to 9. So this one was the first one, where it was Z equals to, the 9 is here. Z equals to 9. It will be this one. And then at this point, this is Z equals to 2. At that point, that strip. So you can see that the orientation of this surface is up. Then the curl is clockwise, anti-clockwise, sorry. And the curl, this orientation of this one is facing downwards. Then the curl has to be clockwise. So you must know those things.
Did you send the solutions for that question paper? Just for me to go.
No, this one I sent for Stokes theorem for now. For the whole question paper, I will also forward. After we are done with physics, then I will compile and forward. However, I was
asking that can I also have notes for today's question?
This one,
the question 7, yes.
I can't hear you.
For question 7 as well. Notes for question 7.
Or notes for question 7 as well. All right.
So what are we going to do? Did you see on the scope that I gave you, they said the type 1 and type 2 region it's gonna come. That's why I was asking that we start with question 4.
Yeah, but this one is not also difficult. This is Stokes theorem. They're just repeating the same thing, that they're just playing around with the values. That's why I said let me also do 2 of those questions. Then you can see the difference in their what was it? Like here they just changed the value here and there. They did not change anything much for this one. Like,
Yeah. At least we know we are done with that question because always it's gonna be there. Yeah. Okay.
let me forward you this one which we're doing for Stokes theorem. Very easy. You can scoop all the marks.
Ah,
Very easy.
can you please take a break? You have
So for what is it? For calculus. I mean for classical, what are we doing today?
I really we spoke that we're not gonna do calculus this week. I mean classical. We were gonna do that one.
Which one?
2602 and calculus because I'm going to write this on Friday and also that one on Monday.
So today we are doing 2602.
Yeah, or we can continue with calculus if you don't mind. I don't have a problem because this one is a challenge to me. I'm
All right.
worried about calculus. We can proceed with calculus.
All right. So let's take the session for classical. We continue with calculus. It's fine.
Yeah. Okay. Thank you.
All right. So let's go to the second one so that you see what was the. Are you still there? Hello. Hello. Hello.